Hi everyone, we are Group 13 enrolled in Chemical Engineering at University of Waterloo. Our design project targets an ongoing concern for humanity, which is carbon emission control. In the hopes of mitigating carbon emission, we are optimizing a type of carbon capture and storage technology called chemical looping combustion, also known as CLC. CLC poses many benefits in improving thermal efficiency of combustion as it provides carbon capture in its intrinsic form. Overall, the project is to optimize a given model from our supervisor to observe the proximity of CLC commercialization while comparing it to the Vienna model. The optimization should abide by the financial and environmental incentives while meeting the power demand for the end users. Current design focuses on the following four major principles: hydrodynamics, mass balance, energy balance, heat transfer. Within these areas, the design focus will be determining the optimal operating conditions, process setup, and for direct measurables such as solid conversions and the input-output mass flow rates. Our design constraints are based on the proposed model to reiterate the working model to optimize. We will be operating at 1000 Kelvin and 10 bar with the most efficient oxygen carrier while meeting the health and safety protocols of CLC process. Also, the design model should output results that are aligned with the published literature data. The criteria for a successful project are to generate 100 megawatt of thermal power while achieving less than 15% of carbon monoxide and 5% hydrogen gas conversions. In addition, it is in our aim to minimize the operational and capital cost of the process. And now, Elliot will explain how we establish these constraints and success criteria based on literature reviews.
In the last decade, significant progress has been made towards a better understanding of the world climate and of the long-term impact of climate change. Chemical looping combustion, as a newly developed technology for carbon capture and storage, is a promising method to decrease the emission of carbon dioxide significantly from coal-fired power plants. Based on a variety of literatures that we have reviewed during this project, a common chemical looping combustion usually involves the use of a metal oxide as an oxygen carrier, making a closed cycle between two interconnected reactors of the unit. There exists certain criteria for the oxygen carrier relevant to environment, thermodynamic properties, reactivity, etc. After much consideration and researching on various literature, we are using ilmenite as oxygen carrier in our project. As for the operation unit, a 1D hydrodynamic model has been used as a reference and run under plug flow conditions for both air and fuel reactors, which are the two main units for the operation. For the relevant regulations or legislation, the Intergovernmental Panel on Climate Change, which is IPCC, provides the argumentation that the increase in anthropogenic greenhouse gas concentrations back in most of the observed increase in globally average temperatures. The International Environmental Agency, which is IEA, raises standards for any criteria related to environmental protection and provides support to the necessity of chemical looping combustion.
So for problem work breakdown structure, the very first step, which is identify the works that need to be done, we have broken them down into three phases. First is preliminary. That includes a project planner for our supervisor that indicates the detailed instruction and timeline for each test. Also literature review with references in last year's report, optimization models or how we should optimize, and share and organize what we find. The preliminary is set to take place between May to mid-July. Second of all is the intermediate step, which will involve discussion with the supervisor on how to start on Pyomo modeling, receive previous codes from the group before us, investigate the discrepancy, and then learn how to use GitHub and Bitbucket, because that is an essential tool when it comes to pushing and pulling codes. That is set to take place between July and August. Last of all, we'll have the finalization phase, which includes optimization models, exploring and carrying them out. That will take place around January to April. So the work structure will be mainly broken down into three parts. First is the literature review that needs to be completed by each individual member. We will have bi-weekly meetings with our supervisor to sync up on our progress, and then we assign corresponding group works to each member. of the team. In order to track completeness, we quantify that by assigning a percentage to each task. For success criteria, if we achieve a model with an error that is less than 15 and 5% for the carbon monoxide and hydrogen gas conversion respectively, we consider that as a success because that is the discrepancy obtained between last year's report and the Vienna circulation scheme model. So here is a glimpse of the current project plan. We'll have 4 main stages: initiation, planning, execution, and closeout. For the first phase, we will review last year's group report and then all the relevant literature review. These will take place between May and the second week of July. Then we will sync with our supervisor and then learn the necessary engineering tools required for this project. Moving on into planning, which is set to take place between the third week of July until the second week of September, we will propose possible approaches to solve the problem, have programming responsibility broken down. We will audit the Pyomo codes that was written earlier, look for the source of error and identify the main contributor, and then figure out the parameters that we are going to model. Third, which is execution, that is mainly composed of code modification, optimization modeling, and model deviation comparison. We are adding more tasks to the execution phase as we go. However, execution is set to take place starting in 2021.
Based on process safety management, we are using what-if hazard analysis method. Since the operation unit itself and the composition of vent gas are quite simple, the whole process mainly includes 2 hazards. One is the considerable heat during the process, since it is a combustion process. The other is the ilmenite, which is the oxygen carrier being used. For the ilmenite, hazards may occur if skin contact, inhalation, and ingestion happen. Ilmenite is classified as carcinogenicity 1B and has specific organ toxicity. Inhalation of ilmenite would cause cancer, and respiratory irritation while skin or eye contact would cause serious irritation as well. If inhaled, one must be moved to fresh air and kept comfortable. If after contact, contaminated cloth must be removed from victim and the contaminated area must be washed with plenty of warm water and soap for 15 minutes. Thus, ilmenite must be stored in a well-ventilated place in properly labeled, tightly sealed, appropriate packaging. As for the heat generation during the process, heat would be leaking if the valve connected to any of the reactor is leaking. If burning injuries occur, there will be redness with or without blisters on the skin. The injured area should be performed with cool water 10 to 25 degrees Celsius, and early cooling reduces burn depth and pain. Therefore, the reactor and the valve must be inspected on a regular basis, and any obsolete part must be replaced immediately.
The engineering tools that are selected for this project are the Python Pyomo library for optimization and Git and Bitbucket for sharing codes. The Pyomo library is a collection of Python software packages for formulating optimization models. It provides a diverse set of equation-oriented optimization capabilities with high degree of modeling flexibility and intuitive syntax. MATLAB and GAMS are also adequate choices of software for this project. However, Pyomo is more suitable than MATLAB for optimization problems. GAMS has similar performance as Pyomo, but the group members were more familiar with using Python than GAMS. For collaboration of codes, Git and Bitbucket were selected. Git is a distributed version control system for tracking changes in source code for software development. It facilitates management of changes by different contributors. Bitbucket is a web host that uses Git, and it allows all the group members to contribute online. These engineering tools would allow us to solve and optimize the system in an organized and efficient manner.
So, that is the end of our presentation. We are hoping to gain personal knowledge as well as make a meaningful contribution to the world with this design project. Thank you all for listening. The references that are associated with the literature review are located here.